All right, this is our model of polymer, right? These strings I've got here are meant to be molecules, individual molecules in a polymer. And what I'd like to do is I'd like to consider in the next few videos some ways that we could make a polymer stronger. So if we think about making plastically deforming a polymer, we remember that we've got to have the ability for chains to slide past each other. These molecules slide past each other. And you can see in this jumble of strings I've got here that it's very difficult to grab a chain and pull it out because you get all this entanglement. And that's actually something that happens in a polymer. We call it entanglement. Yeah. And so how could you make a polymer stronger? Well, one of the ways I think is quite apparent from this model is by making the molecules really long. You could think about eating a bowl of spaghetti, pho, udon, ramen, you name it, and you take a little one, try to take one noodle out. Well, you pick up most of the bowl because the noodles are all twisted in amongst themselves. And if on the other hand you wanted to feed noodles to a baby, you would go in there with a pair of scissors, right, and cut them up. And then you could just take a spoon and separate out a few of the short little noodles very easily. Well, the same thing is true in a polymer. And so by making the molecules longer, we can increase the strength. But what I'd like to do is now explore how are we going to quantify how long these molecules are. And one of the challenges with that is that the molecules are not linear. We might refer to a molecule like polyethylene like this as being linear. It's roughly a straight line, but you can see along the backbone there's actually a zigzag, right? The carbon-carbon bonds zigzag back and forth like this, and then on top of that you can get bond rotation, and so they get all twisted like this, which is how we arrived at this jumble being what's commonly present inside a polymer. And we'll look at cases where this actually becomes organized later, but for now this is pretty good. So length seems to be maybe a challenging way to describe a polymer, and I want to present you with an example. Say I gave you a box, okay, I gave you a box as a puzzle, and so this is a box, right? It's not a unit cell this time, and that is a box, and it's in fact not just a box, but it's a box of rope. Okay, in fact there's one single piece of rope in there. So let me draw that rope in for you. Maybe it's a blue rope. Okay, there's one great long piece actually. Okay, one long rope, one piece. Okay, but what do you know about this? The only thing I give you is the mass of the contents. And say it's actually an opaque box. That is, you actually cannot see into it. Okay? But I ask you this question. I ask, how long is the rope? You can't open the box. I won't let you. Right? I'm a jerk like that. I won't let you open the box, and I want to say, how long is the rope? Well, at this point, with just the mass of the contents, you have no way of knowing. But if I gave you this little piece, if I said, okay, look, here's a little piece of the rope that is, it has a length of, say, 1 meter, and I give you for that rope the mass per unit length, per meter perhaps. So we'd actually have, well, I should be careful here, mass per length, or units, say, of grams per meter, right? Mass per unit length. Well, you appreciate now you could, with the mass of the contents, easily tell me how long that rope inside the box was. So what we've used in that little thought example is we've used mass to describe length, right? And that's exactly what we do for a polymer, except we call it the molecular weight. And at this point, we can really think of molecular weight as describing chain length. That is, if you've got a high molecular weight, you've got extremely long chains. Low molecular weight, they're shorter. And so I'm going to give you an example here. A neat example is ultra-high molecular weight polyethylene. And where is it used? Well, in one place it's used is in hip implants, hip replacements. All right, hip replacement. So if you have an older relative perhaps who broke their hip, well, the what the orthopedic surgeon could do is right, the top part of your thigh, right, is the femur, and that articulates with your pelvis. And so they just lop off the top of the femur. They cut that off, they replace it with a metallic component. So there's this stem of the femur, and it articulates with this acetabulum. So you get metal that would be rubbing against your articular cartilage. And what will happen there is it'll wear away pretty quickly and migrate up into your hip. So what orthopedic surgeons do is they'll actually replace the portion in the pelvis, the acetabulum, with a piece of ultra-high molecular weight polyethylene. And that's used because it is high strength, and we can appreciate that by thinking about that molecular little hand. It's difficult to pull one chain away from the others because there's a lot of entanglement, okay? So it's high strength, and it has good wear resistance as well. It's also, it turns out, well tolerated in the body and doesn't induce these foreign body responses. So anyway, that's just a quick example of molecular weight, and we can certainly increase the strength. It's an important strengthening mechanism, increasing the strength of a polymer by increasing molecular weight. Okay, thanks a lot.